Hi, and welcome to Sequences and Series. Hopefully by now you've watched the video that introduces Taylor polynomials by 3 Blue 1 Brown. I think that does a really good job of explaining what we're trying to get to with sequences and series. But of course, before we get to finally being able to build these Taylor polynomials, we need to start at sequences and get to there. So what is a sequence? Well, a sequence is just a list of things where the order matters, right? Where order matters. So if we have a mathematical sequence, it's going to be written like a sub 1, comma a sub 2, a sub 3, to a sub n, and these are called the terms, right? These are called terms, and a sub n is called the nth term, okay? The nth term. And there are a few ways that a sequence can be expressed. It can be expressed by an ample number of terms separated by commas. What's an ample number mean? It means a number that's enough for you to be able to recognize the pattern. So we could have like 1, 2, 3, 4. Okay, that's probably plenty. I think you can see the pattern there. We're just adding 1. It can also be an explicit function defined by the rule of the sequence. So you could have like a sub n is equal to n plus 1, right? Okay. So you could also have the rule of sequence set off in like braces. So you could, instead of writing it this way, write like n plus 1. Or finally, you could just write that actually in the list. So you could have like 2, 3, 4, comma, n plus 1. So these are actually the same, number 2, 3, and 4. Those are all the same sequence, actually. All right, so let's do a few examples here. The sequence 2, 4, 6, 8 is the sequence of even numbers. We're asked to express the same sequence as a rule of non-negative integers n, okay? So we have 2, 4, 6, 8, and we want to figure out how we can write that as a sequence using the integer n, right? So this is our first term. This is n equals 1, n equals 2, n equals 3, n equals 4, right? So if at the first term n is equal to 2, at the second term it's equal to 4, third is 6, fourth is 8, I think we can see here that our pattern is just going to be 2n, right? So we can write it 2n, and we can also write it like this. What about, we're going to have to do the same for the sequence 1, 3, 5, okay? Well, if we have 1, 3, 5, well, if these are our odd numbers, this is our first term, this is n equals 1, this is n equals 2, n equals 3. Well, it looks like that's going to be the same kind of as our even numbers, right? 2n, but we have to make it so that our first term, instead of just being 2n, actually becomes 1 again. So we're going to have minus 1. So that's our pattern for our odd numbers. Okay, let's do some more examples here. If a sub n is equal to 4n over 3 plus 2, we're asked to list out the first 5 terms, then estimate the limit as n approaches infinity of a sub n. Well, we can write out our first 5 terms, and I actually like to do it like this. So I like to write a sub 1, a sub 2, a sub 3, a sub 4, a sub, oops, I wrote 5 sub 5, a sub 5. That's just how I like to do it. But you can, of course, list them out in a row as well. That's fine. So a sub 1, we're going to have 4 over 3 plus 2 is 4/5. A sub 2, it looks like we're going to have 8/7. A sub 3, we're going to have 12/9. Ugh, I didn't really leave myself enough room here. A sub 4, we're going to have 16/11. And a sub 5, we're going to have 20/13. Okay? So these are our terms. And you can see here that like a sub 3, that could be simplified, but a lot of times with sequences, they're not, so that you can get a better idea of what the pattern is. If we were to simplify that and reduce that fraction, we'd kind of lose the vision of the pattern. So a lot of times it's just left like that. And so this goes on and on, So now we're asked to find the limit. So the limit as n approaches infinity of a sub n, well, a sub n, why did I write that? Of 4n over 3 plus 2n. Well, that limit, if I calculate this limit, I'm going to 4n over 2n, these n's are going to cancel out, I'm just going to get 2. So this actually means that this particular series, as it gets larger and larger and larger, as we're going adding more and more terms to infinity, I shouldn't say it's getting larger, we're adding more terms to infinity. As that happens, the sequence is getting closer and closer to 2. So we say that it converges to 2. Okay? So there are a number of possibilities that can happen when we have a sequence. So let's say a sub n is our sequence. Well, as we add an infinite number of terms, it can go to infinity, which means it diverges. It could go to negative infinity, which means it diverges. It could go to some c, a constant. That's when it converges. Like that's what we just had. So it converges to some constant c. Or it could oscillate between two fixed numbers, right? So let's say that you ended up having a sequence that was something like 2, negative 2, 2, negative 2, 2, negative 2, on and on and on. Well, that's just bouncing up and down, up and down, up and down. That's oscillating, and when it oscillates, it diverges. It never converges, okay? So let's talk a little bit more about series converging or diverging, but before we do that, I just want to give you a little refresher about this term here. This reads as n factorial. Hopefully you remember factorials, a very exciting look in mathematics. Do you get that joke? Because it's an exclamation point. So n factorial is equal to n times n minus 1, the previous term, times n minus 2, the previous term, times n minus 3, the previous, all the way down to 3 times 2 times 1. Okay, so if I had like 4 factorial would be equal to 4 times 3 times 2 times 1. Okay. And factorials are used in statistics if you're in stats class, how to find the number of possibilities of ways to arrange things. All right, so we're going to be using those as we progress. But let's find out if these following sequences can converge or diverge. So here we've got 1/2, 2/3, 3/4, 4/5. Well, we've got n over n plus 1. Let's use and actually find our limit here. So our limit as n approaches infinity, because we can use our limit to calculate if this converges or diverges, of n over n plus 1, looks like that's just going to equal 1, so this converges to 1. Okay? For letter B, we've got 1/2, 1/4, 1/8, 1/16, goes to 1 over 2 to n. So we can again find our limit as n approaches infinity of 1 over 2 to the n. Well, that is going to grow very fast down here in our denominator, so this is just going to go to 0, so this converges to 0. Now, I want you to note, this sequence does not equal 0 as a value. It just converges to that. That's why limits are so important here, okay? Letter C, we have 3 plus, this is a plus sign, negative 1 to the n. Okay, well this one's a little bit awkward to see, so let's actually do this. So 3 times negative 1 to the first would be 2. 3 times negative 1 to the second would be 3 plus 1, which would be 4. So this would be 2, 4, 2, 4, on and on and on. What's going to happen here? This is oscillating. So this diverges by oscillation. All right. Let's look at D. A sub n is equal to n over 1 minus 2n. Well, I'm not even going to write our limit here. Just tell me what's going to happen here. Well, this is going to converge to a negative 1/2, right? Let's do a few more. A sub n is equal to the natural log of n over n. This is a good time to remember the order that our, like, what do I say? Functions grow. So our slowest one is going to be like an integer k, right? Then we're going to have log base n is a little bit faster. Then n to the a is a little bit faster. Then b to the n is a little bit faster. Then n factorial is even faster. Then n to the n is even faster, right? So these are our slowest ones, these are our fastest ones. So it looks like here, that's a log, looks like here we have something, something slow, but this is slower, or this is faster, right? Our denominator is faster. So if we have slow over fast, we are going to, this is going to converge to 0, okay? Look at letter F. We have a sub n equals n factorial over n plus 2 factorial. Well, I can rewrite this a little bit to be n factorial over n plus 2, n plus 2 times n plus 1 times n factorial, right? So now these cancel out. So I'm going to have 1 over n plus 2, and it was 1 over basically infinity if I was going to find a limit here. So this converges to 0. All right. Let's do another one like that. Letter G, 2 factorial over n minus 1 factorial. Well, I can rewrite this as 2n times n minus 1 factorial over n minus 1 factorial. Those are going to cancel out. So then we have 2 times infinity. So this diverges to infinity. Okay. Letter H, a sub n equals n plus negative 1 to the n power over n. Well, I can rewrite that as n over n plus negative 1 to the n over n. And this negative 1 to the n over n, that's just going to basically become 0, right? 0. So n over n, this is going to converge to 1. Converges to 1. Letter I. We have negative 1 to the n times n minus 1 over n. Well, this one is similar to one we did earlier. Just think here, if you have negative 1 to the n and you start writing out your terms, you're going to have negative, then positive, negative, then positive, negative, then positive. What's going to happen here? This is going to oscillate. So this diverges by oscillation. Okay? Letter J, we have this over this. If we go back here to our list of factorial is faster, so this converges to 0. K, this one's a little bit complicated, but let's do it here. We have a sub n equals 1 plus 1 over n to the n. That is going to be, what's the word? What's the word? Let me pause. Indeterminate. I figured out the word. This is an indeterminate form. And you might remember back when we were talking about L'Hopital's rule, I think it was like 2 chapters ago, talking about indeterminate forms. So let's actually do it this way. So we have y is equal to the limit as n approaches infinity of 1 plus 1 over n to the n. And if I take my ln, so I've got the ln of y is equal to the limit as n approaches infinity. Now, this n I can pull out front here of n times the natural log of 1 plus 1 over n. Okay, so now I can rewrite, this is still an indeterminate form, I can still rewrite that. So the ln of y is equal to the limit as n approaches infinity of the natural log of 1 plus 1 over n to the negative 1. Now you would take L'Hopital's rule, so you would get ln of 1 is equal to the limit as n approaches infinity of 1, that's not what I wanted yet, 1 over 1 plus 1 over n times negative n to the negative 2, or negative n to the negative 2. These are going to cancel out, so then you're going to end up getting, and this actually goes to 0, so you end up actually getting y is equal to E, right? So this is a definition of E. E is equal to the limit as n approaches infinity of 1 plus 1 over n to the n. That's a definition of E right there. And we can say that this converges to E. What a mess, right? All right, what about here? We have 2n factorial over n to the n power. Again, that chart that I made of slowest to fastest, this one is just going to converge to 0. Okay? All right, let's keep going a little bit. Sometimes we're also asked to actually write an expression for our sequence. So here we have 3, 8, 13, 18. We want to actually find that pattern. And I think looking at this, you can maybe see we've got plus 5, plus 5, plus 5. This is actually called an arithmetic sequence because we're adding and subtracting. So if we keep adding 5 multiple times, we are actually multiplying, right? So this is going to be 5n. But if you look at this, 5n is, if I have n equal to 1, well, it's actually 5, and my first term is not 5. My first term is 3. So my first term is, or my nth term is actually going to have to be 5n minus 2 in order to get that correct term, right? Okay, let's do another one. Here we have 5, negative 15, 45, negative 135. I think here you can see that this is actually multiplying by negative 3 times negative 3 times negative 3 times negative 3. Okay, so I find with this type it's easiest to kind of factor out a common factor if you can, and I'm going to do that right now. So I've got 5, 15, 45, 135. I can take out a 5, and I'm going to end up with 1, negative 3, 9. Oh, what's 135 divided by 5? Something good. 27, right? Negative 27, dot, dot, dot. Okay. So now let's look here. My n, it looks like I'm just taking n times negative 3, but it's not times negative 3, sorry, but negative 3 to a power, right? So I guess it is kind of times negative 3. So times negative 3 times negative 3 squared times negative 3 to the cubed, blah, 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 blah. So this is going to be negative 3 to the n power. But if I have negative 3 to the first power, that's actually negative 3. That's my second term. So I'm going to need to subtract here in order to get 0, right? So this is negative 3 to the n minus 1 power. And don't forget this 5. Put that 5 back there, and we've got it. We've got our whole thing. All right? Let's do another one here. 1, 4, 9, 16, 25. Hopefully you can look at that fairly easily and see that this is n squared. All right? 4, 10, 28, 82. Well, this one's a little bit awkward. If I look here and I have 4 times 2 is 8, 4 times 3 is 12. Okay, 4 times 4 is 16, 4 times 5 is 30. Looks like I'm getting some interesting things here, but actually I'll kind of give you a hint here. If we look at this in terms of 3, right, this would be 3 to the first power plus 1. This would be 3 to the second power plus 1, 3 to the third power plus 1. So our pattern here is actually 3 to the n plus 1, which is kind of a cool one. Here we've got some fractions, so we can think of those as two separate terms. So in our first one, we've got 2, 3, 4, 5, 6. That's just going to be n plus 1. In our bottom, we have the odds, which we already saw, so that's 2n minus 1. And for f, our last one here, we've got ln of 1, 2, 4, 8. So I think it's going to be the ln, a sub n, is equal to ln of, looks like we're going to have 2 to what power? Well, if this is our second term, then we're going to have 2 minus 1, so that should be n minus 1, right? Okay, one last thing I want to talk about. We have a theorem that can help us determine whether or not a sequence will converge. That theorem states, if a sequence, a sub n, is bounded and monotonic, then it converges. Well, what does it mean to be bounded and monotonic? Monotonic means it's non-decreasing or non-increasing, meaning each term before it is less than the previous one, or each term is greater than the next one. Basically, it's just either only increasing or only decreasing, right? And bounded means that all these terms are greater or less than a real number m. You'll actually see that they're like tight and bounded by a number. So let's look at a few of those. Okay, so here we're given this. What's happening here? We're going to determine, we want to determine if this is bounded, monotonic, and convergent, right? So if we have both of these, we're going to have the last one here. So is this bounded? Well, actually, yes, it is. This is bounded at 0, right? Is it monotonic? Is it strictly increasing or strictly decreasing? Yes, it's monotonic. It's decreasing. Decreasing. So if it's bounded and it's monotonic, then it's convergent. So it converges where? Converges actually to 0 in this case. These are just rough graphs, but hopefully you can kind of see. Here, is this bounded? Yes, this is actually, I don't know, 5, 6, we'll call it 6. This is 6 here, and it looks like we're going to kind of cap out here. So this is bounded at 6. Is it monotonic? Is it strictly increasing or decreasing? Yes, it's monotonic. It's increasing. So is it convergent? Yes, it converges to 6. Okay? What about this one? Well, here, it looks like our function is going up or down, up, da, 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 da. Is it bounded? Yep, actually it is. It is bounded. It's bounded here and here, right? I don't know what those values are, but it is bounded. Is it monotonic, though? No, it's not monotonic because it's increasing and decreasing. Therefore, it's divergent. And this is divergent by oscillation, right? This is oscillation in action, right? What about this here? Is it bounded? Well, it looks like it kind of is bounded. It's bounded below. It's bounded below right here. But is this monotonic? Yes, it's monotonic. It's increasing. But is this convergent? Now, I didn't give you a very clear definition because even though this is bounded and this is monotonic, because it's strictly increasing and it's not bounded during the increase, this is actually divergent. And I hope that you're able to see that. Like this is increasing on to infinity, so it is divergent. It's not actually convergent. All right, that's all I have for sequences. Hopefully all of that made sense. I look forward to seeing you soon. Bye.